Hey everyone, welcome! Today we're diving into what I like to call a data detective journey. Our main mission here? To completely demystify data science. I mean, we live in a world just absolutely overflowing with automation, cloud computing, and AI, right? And because of that, it is so incredibly easy to just plug some information into an algorithm and, well, hope for the best. But today, we are ripping the lid right off that process to really understand the mechanics underneath it all. Look, before anyone, and I mean literally anyone, can successfully apply complex machine learning algorithms, they absolutely have to understand the structural building blocks of data manipulation. Think about it. You wouldn't build a massive skyscraper on a totally shaky foundation, right? Well, you certainly can't build a reliable predictive model if you don't fundamentally grasp the shape, the type, and the quality of the raw information you're actually feeding into it. Our whole philosophy for this explainer basically boils down to a pretty simple warning. Sure, some folks might be perfectly satisfied with only learning how to use off-the-shelf recipes, but what if the assumptions of that black box recipe are violated? Relying blindly on automated AI tools is a massive, massive risk if you don't get the underlying structure. If your data violates the assumptions of your software's recipe, your results aren't just slightly off, they can actually be dangerously misleading. We really have to know the math and statistics behind the curtain. So, to make sure we don't fall into that trap, here's our game plan. First up, beyond the black box. Then, importing the raw data. Third, structuring by feature type. And finally, summarizing and visualizing. All right, let's jump right into part one, beyond the black box, and take a look at the data pipeline. Every typical data science project generally follows 4 standard steps. You start by gathering data to learn about a specific question. Then, there's cleaning and summarizing that data. Next comes the actual modeling and analysis. And finally, translating those models into real-world decisions and predictions. Now, since this explainer is all about building that rock-solid foundation we talked about, we're going to focus heavily on those crucial first 2 stages, gathering and cleaning. Moving right along to part 2, importing the raw data. Or, as a data detective would call it, stepping into the crime scene. Okay, so here is the absolute fundamental definition we need to get straight. Data is generally the outcome of a random experiment. It's an experiment where we can't determine the exact outcome in advance, but we can still analyze how it works. In a normal spreadsheet, your variables are called features, and they're stored as your columns, while the individual items or subjects are your rows. Those feature columns could be unique identifiers, they could be experiment designs, like, which test group someone is in, and they can include highly variable measurements that would completely change if you ran the experiment again. So, how do we actually get our hands on this raw evidence? Well, we can pull these raw files straight into a Python data frame. Using the pandas package, a really simple read_Excel command just grabs an Excel file directly from the internet. Throughout our explainer today, we are going to be tracking the results of a real-world nutritional study involving 226 elderly individuals. It's fascinating stuff, and using simple code like this is exactly how we pull that messy, real-world evidence into our workspace so the interrogation can begin. Okay, part 3. Structuring by feature type. It's time to identify our suspects. We're basically looking at 2 main types of data features here, quantitative on one side and qualitative on the other. Quantitative features possess actual real numerical quantity. Think a person's height or their age. These can be continuous, taking values across a precise range, or discrete, like a totally countable number. Qualitative features, on the flip side, have absolutely zero numerical meaning. They are purely categorical. A really handy rule of thumb I love to use is this. If it doesn't make sense to average the data, it's qualitative. Like, you can average out a group's height, sure, but averaging their eye colors? No way. That makes absolutely zero sense. Let's actually ground this in that elderly nutrition study we just brought in. Think about the qualitative features, things like gender, family situation, the kind of cooking fat they prefer, or how often they eat meat, fish, or chocolate. Even if we code these with numbers in our system, say a 1 for butter and a 2 for margarine, those numbers still have zero quantitative meaning. Then we've got our discrete quantitative features, like the exact countable number of cups of tea or coffee they drink daily. And finally, continuous quantitative variables, their exact height, weight, and age. Getting this classification right is totally non-negotiable for what we do next. Which brings us to part 4, summarizing and visualizing, the interrogation and sketching phase. Now, to find the exact center of our data, we use tools like the sample mean, the median, and quartiles. But here's the catch. Knowing the center is practically useless if you don't understand the spread. For that dispersion, we rely on the sample range. the variance, and the standard deviation to really see how far those values stretch out. These metrics tell us the mathematical story of our data way before we ever even think about drawing a chart. And then, boom, we hit that critical aha moment, that brilliant spark of illumination that comes when we finally step away from dry summary tables and begin actual visual plotting. Visuals are where the hidden patterns just jump right out and the true story of the data reveals itself to us. But hold on just a second. Before you start furiously drawing up charts, there is one absolutely unbreakable rule in data visualization. The type of plot you choose relies entirely on whether your variable is qualitative or quantitative. If you use the wrong plot for the wrong data type, I guarantee you'll just end up creating a meaningless, confusing mess. All right, let's unpack this rule a bit. For qualitative variables, your absolute go-to tool is the bar plot. Since qualitative data is categorical, like whether our elderly subjects live single, as a couple, or with extended family, we want to show the frequency or the total count of each category. A bar plot does this flawlessly. It draws rectangles where the height directly represents the number of people in that specific category. It's clean, it's totally accurate, and it fully respects the fact that these categories don't have any inherent numerical order. Now, for quantitative variables, on the other hand, like, say, our subject's specific ages, we need entirely different tools that show the spread and shape of that numerical variability. Enter box plots. A box plot draws a box from the first to the third quartile, it marks the median right inside, and extends these little whiskers out to show the range, all while plotting any weird outliers as individual dots. We also heavily use histograms. A histogram takes a continuous range of numbers, breaks them down into evenly spaced bins, and tallies up the count of values falling into each one. It just perfectly captures both the central tendency and the exact shape of your data's variability. So after walking through this whole meticulous process to finding data, importing it, categorizing it, and visualizing it by some pretty strict mathematical rules, I want to leave you with a final, kind of provocative question. We are living in an era where everyone is just rushing to push raw data into these hyped-up AI tools. But if the assumptions of your black box algorithm are violated just because you didn't truly understand your feature types, can you really still trust the results? I hope this explainer has shown you why the answer is a resounding no, and I really hope it leaves you hungry to dig deeper into the statistical mechanics that actually power data science. Thanks so much for learning with me today.